Welcome to Almost Sure. Recently, I've been hearing talk about negative probabilities. It seems to have started from an interview with this
We
guy.
even had, at some point, people using negative probabilities.
Can this be true? Can a probability be negative? Surely not. But that's what I'll look into here. Let's check back with Nassim Taleb, see what he's got to say.
Like something that has one attribute that it's a derivative of something that's never decreasing.
It's the derivative of something that's never decreasing? So it's never negative then. Okay, let's take a step back. What even is a probability? This is something that we could argue about forever. But mathematically, it has a precise definition according to Kolmogorov's axioms. It is the value assigned to an event by a measure, which, by definition, cannot be negative. But the mathematical definition is just an attempt to model or formalize a real-world concept of the level of certainty of an event happening. Take the frequentist interpretation, for example. An event's probability is the limit of its relative frequency in infinitely many trials. So if we repeat the trials a big number n of times and the event happens in m of them, then the relative frequency is m divided by n. This is a number between 0 and 1. Even if we take the limit as n goes to infinity, it can't approach something negative. So no, probabilities still can't be negative.
And smart people understand that, yeah, you can use negative probability because it's a kernel.
Okay. We is smart people. So let's get to the bottom of this. Now, Paul Dirac, he said that negative probabilities are well-defined concepts mathematically, like a negative of money. Richard Feynman also mentioned that negative numbers of, say, apples can appear in the intermediate steps of a calculation, even though the final answer must be positive. In the same way, negative probabilities can occur. Now, Dirac and Feynman, they are smart people too. Let's think about this a bit more. An observable event can't have negative probability, but maybe unobservable events can. Okay, the probability of an event which can't even be observed, well, that has no real meaning, but maybe it can be useful. In fact, we do this type of thing all the time, using probabilities which cannot be observed. For example, suppose we have a microscopic particle diffusing in a fluid, and we want to know the probability that it hits a detector. We can sum up the probabilities of every possible path where it reaches the detector. Even though we might not be able to observe these individual paths, maybe it's even impossible to observe. We just see whether or not it reaches the detector. But summing up the probabilities still makes sense. And potentially, maybe, some of these unobservable paths could have negative probability. As long as when we sum over them all, we get a positive result, there's no actual contradiction. The negative probability paths would just decrease the probability of hitting the detector. But in what situation can some paths have a negative probability? It's difficult to see how that could possibly be the case.
Just like in quantum mechanics, they use negative probabilities.
Quantum mechanics. Of course. If we're looking for weird, counterintuitive stuff, quantum mechanics is the place to look. Okay, I joke a bit. I don't think quantum mechanics is half as weird as people like to make out sometimes, but it is somewhere where negative probabilities sometimes appear. Well, maybe they do. By the way, those clips of Nassim Taleb that I've just been showing, they were his response to a question of how to tell if somebody understands probability. and the slightly garbled discussion of negative probabilities and kernels with unclear context maybe wasn't the best response. So unsurprisingly, it did lead to a bit of ridicule online, but there is a kernel of truth.
So, and our option traders don't talk about probabilities.
Oh, really? Okay, I'll take it from here then. Maybe you've played around with polarizing filters before. A single filter will block out half of the light that shone through it. Another filter in front of this does not make much difference, but rotate it 90 degrees and bye-bye, all of the light is blocked. The explanation for this in terms of particles of light or photons is that they come in two polarizations, either horizontal or vertical. The first filter blocks one of these, say the horizontal, letting the vertical ones through. The second filter, angled one way, also lets the vertical ones through, but rotated by 90 degrees, and now it only lets horizontal ones through. So in that case, all of the photons are blocked. Both the horizontal and the vertical polarizations are blocked by one or other of the filters. Actually, I think I'll just put one of these on the camera. Okay, good. Now that's done. If I take a filter and I hold it up with the same orientation as the one on the camera, then we see that light goes through it. And if I rotate it 90 degrees, then once again, we see that it blocks the light. But if I bring in another filter and I put this at an angle, whoa, some light comes through now. Take that away. See, one extra filter lets more light through than just having the two, the one here and the one on the camera. So what is happening? If this was just blocking photons, then that wouldn't be possible, right? Maybe it's blocking photons that had a negative probability of getting through, and that just leaves the ones with a positive probability. Okay, that seems a little weird, and more likely this middle filter is simply modifying the photons so that now they can make it through. Who knows? Let's look a little closer at light. It consists of electromagnetic waves, so it has oscillating electric and magnetic fields, and these are perpendicular to each other and to the direction of travel of the wave. When we talk of the polarization of light, this refers to the direction of the electric field, which can be along any axis perpendicular to the light beam. The polarization of a single photon, though, that's probabilistic in nature and represents the smallest possible amount of quantum information, a single qubit. If it's measured in the vertical direction, then it either has this polarization or it doesn't, in which case it's horizontal. So it's in one of only two possible states. Yes, you can measure at different angles, but those polarizations are just superpositions of the horizontal and vertical cases. If a photon is vertically polarized, but you measure at an angle theta to this, then the probability that you find it with this new polarization is cosine of theta squared. And the probability that you don't find it in this polarization, meaning that it's perpendicular to that, well, that probability is sine of theta squared. And cos squared plus sine squared equals 1. So with 100% probability, you find it in one of these two polarizations. For example, suppose we hold two filters at a 60-degree angle to each other. As cosine of 60 degrees is a half, cosine squared is a quarter, so only a quarter of the photons that pass through the first filter will pass through the second. So let's see. They're both at the same angle. Let's rotate by 60 degrees. And yeah, it goes pretty dark. This suggests an interesting experiment. Suppose we hold the filter vertically, so half the photons will get through, I'll call this measurement A. For each photon, A equals 1 if it goes through, so it's vertically polarized, and A equals 0 if it doesn't, so it is horizontally polarized. Let's tilt the filter 60 degrees from vertical and call this new measurement measurement B. If the photon can pass through a vertical filter, then it has a 1 in 4 chance of passing through filter B, as we saw. Also, if the photon isn't able to pass through A, then the probability that it isn't able to pass through B is probability 1 in 4 again. And we can check this. If we go back to filter A and filter B, all we have to do is rotate them both by 90 degrees, and that exchanges which photons they block and which they pass through. But it hasn't really changed the situation, so the probability remains the same. So probability that A equals B is 1/4. Finally, one more measurement. If we tilt the filter 60 degrees from vertical but in the opposite direction, let's call this measurement C. This is exactly the same as before, so that the probability that A equals C is 1/4. But what happens if we compare B and C? So, B and C. One will be 60 degrees in one direction, and the other one is 60 degrees in the other direction. So these filters are 120 degrees from each other. But if you look at the angle in the other way, then it's still 60 degrees from each other. So the situation is still the same. 1 in 4 of the light through the filter B will get through filter C. And the probability that B equals C is 1 in 4. But let's pause and think about this. This is actually pretty odd, as each of the 3 comparisons between pairs of filters has probability 1 in 4. There's at most a 3 in 4 chance that at least one pair between measurements A, B or C are equal. So there's at least a 1 in 4 chance that they're all different. But this is impossible, right? There's only 2 possible outcomes for each measurement, 0 or 1. They can't all be different. But let's ignore this impossibility for the moment and simply calculate the probability that A, B and C are all equal. We can use this expression for 0, 1 valued random variables. The probability that A equals B equals C, this equals the probability that A equals B plus the probability that B equals C plus the probability that C equals A minus 1, all divided by 2. You can check this if you like just by comparing the events on the left and the right in the 2 possible cases where 2 of the variables are equal and in the case where all 3 of the variables are equal. If we plug in our probabilities, probability that A equals B equals C is 1/4 plus 1/4 plus 1/4 minus 1 divided by 2 minus 1/8. So it's negative. Okay, maybe our filters weren't just blocking light, but also modifying it. So when we put the filters, when we passed the light through both filters and measured both A and B, then our measurement of A maybe affected measurement B. So we weren't really measuring the probability that A equals B. But there is a way around this, and that is entanglement. Now, if you shine a laser beam through certain types of crystal, then some of the individual photons of the beam will split into a pair of photons. Although the polarizations will be random, both of the 2 generated photons will have the same polarization. So if one is measured to be horizontally polarized, then the other will also be horizontal. If one is measured to be vertically polarized, then the other will be too. They are entangled. In fact, you can measure polarization in any orientation, and each of the generated pair will be the same. They both pass through the filter, or neither of them do. This method of creating entanglement is called Type 1 parametric downconversion. I won't go into technical details here, The point is that you can have a machine that spits out these pairs of entangled photons. If you're interested though, such a machine can look like this. This is an image from a presentation by Shani Prucci, available on YouTube. So let's suppose that we have our machine spitting out pairs of entangled photons in opposite directions, one at a time, or one pair at a time. And over here we have Alice, who receives one of the photons, and over there we have Bob, who receives the other one. Let's give them both a single polarizing filter, and they check if their photon passes through or not. We suppose that they angle their filter in one of three ways. Each of Alice and Bob can measure the polarization of the photon by holding the filter at the corresponding angle and checking if it passes through. Let's suppose they do measurements A, B, or C by holding their filter vertically, or respectively, at plus 60 degrees or minus 60 degrees to vertical. And this is just as I explained before. A takes the value 1 if the photon passes through and has the measured polarization, and a value of 0 means it's blocked, so it has the opposite vertical or horizontal polarization. Now, it doesn't matter which of Alice or Bob makes measurement A. If one photon is vertically polarized, then so is the other. Remember, they are entangled, so they both see the same result. So Alice measuring A is the same as Bob measuring A, and the same is true for B and C. And as before, if Alice and Bob choose different measurements between A, B, and C, then they have a probability of 1 in 4 of getting the same result. Probability that A equals B is equal to the probability that B equals C is equal to the probability that C equals A, which is 1/4. And if they do the same measurement, then they have a 100% probability of getting the same result. Once again, we can compute the probability that A equals B equals C and get a negative value of minus 1/8, just as we did before. Now, if Alice measures A and Bob measures B, then Alice's measurement can't possibly affect Bob's. They're measuring different photons after all, so it doesn't matter if the filter affects the photon that passes through it. Surely this can't be true, but it is true, and it's predicted by quantum theory, and it's confirmed by experiments. What can we make of all this? What can we make of negative probabilities like these? For one thing, they're not real observable probabilities of anything, and they only appear when we look at simultaneously measuring each of A, B, and C in our case. But this is an impossible thing to do. There's only 2 entangled photons, and making a measurement on any one will change it, so we can't make a second measurement, or we could, but the result might be affected by the first measurement, so it's not the same thing. Between them, Alice and Bob can only make one measurement each. So the property that A equals B equals C cannot be measured. It's just meaningless. And all measurements that can be made in reality will have a positive probability. And it's important to understand that quantum mechanics does not even assign any probability to such simultaneous measurements. And anything it does assign a probability to, it gives a positive probability. Negative ones only entered into the picture once we started trying to infer probabilities or extrapolate the probabilities to unobservable events like this. Also, mathematically, probabilities can't be negative by definition. And the standard thing for mathematicians to do when something does not quite meet the definitions is to add a prefix like quasi or pseudo or semi. And so as to not break the habit of a lifetime, these probability distributions which can go negative are called quasi-probabilities. But even if these negative probabilities only occur for unobservable events, there must be something going on underneath. The photons must have some properties, right, before you measure them. But what is going on? And one way to solve the riddle is to assume some information travels between the photons. maybe the polarizations in directions B and C really are always equal to the vertical polarization A with probability 1 in 4 as the theory said, meaning that they should have a chance of at least a half of being equal. But if Alice measures B, then it sends some information to Bob's photon. So if he measures C, then it adjusts this probability to be less likely to give the same result. But Alice and Bob could be separated by a long way and make their measurements at the same time, meaning this influence must travel faster than light. I mean, they could be miles apart, they could be thousands of miles, millions of miles, light years apart. And we're saying that this influence of measuring Alice's photon, instantaneously affects Bob's photon way, way away. And maybe it even goes back in time if Bob measures his photon first, although in that case we could think of the information going from Bob to Alice instead. And this breaks the principle of locality. That is, any action in any location in the universe only affects the locations next to it, and this influence can spread out, but only at the speed of light. Now, standard quantum mechanics does this by the collapse of the wave function, which instantaneously affects the entire universe as soon as Alice or Bob makes a measurement. And this is some spooky action at a distance. Usually, though, the quantum wave function is not thought of as a real thing. It's just a description of probabilities which only become real when you measure them. And in this way, quantum mechanics is said to break realism. There is a third way out there which doesn't seem to be taken seriously by most physicists, with some notable exceptions.
Superdeterminism.
Maybe the underlying probabilities are not as quantum theory predicts. Maybe A and B aren't really equal for a quarter of the time. Maybe they're only equal for a quarter of the time that Alice and Bob decide to make those particular measurements. Somehow, the state of the photons is affecting what Alice and Bob decide to measure, and this removes some freedom of will. They can't really make their choice independently of the underlying state of the photon, and this is known as superdeterminism. But regardless of what you think is going on underneath, as long as it agrees with the results predicted by quantum theory, then it's just a subjective opinion or interpretation of events and not really science. Now, after I started making this video, I became aware that Sam Gregson and Professor Kajuri had made one on the exact same topic of negative probabilities and also mentioning the comments of Nassim Taleb. And I haven't watched it yet. That's because I prefer to keep this video independent, original content, and not be influenced by what they're saying. So I'll leave the other video in superposition for now. But I will watch it after I finish this and provide a link to it here. Now, the method of negative probabilities or quasi-probabilities, even though it's not standard quantum theory, it can be used in some interesting ways, such as with Wigner quasi-probability distributions, and I might make a video on these, so let me know in the comments if you'd be interested. And experiments like those done by Alice and Bob can be taken further to really show how the supposed weirdness of quantum theory manifests itself. Maybe you'd be interested in a video on this. Again, let me know in the comments. And either way, please like and subscribe, and I'll be back soon with more videos with positive probability, almost surely.